ended last class with this one example here, not finished, number 12 from the class 20 something. So this says that government bonds are often sold based on their future value. So suppose you want to buy a 5-year $1,000 US Treasury bond that pays 4.28% simple interest. This means that the future value of the bond is $1,000. That means that 5 years from now, you'll be able to cash it in for $1,000. So we have to figure out the present value, how much it's going to cost today. So in general, it should cost less, right? Because if you buy it now and you're going to trade it in 5 years later for $1,000, right? You wouldn't do it if it cost more, right? You'd lose money. So hopefully it should cost less than $1,000 today. 5 years later, you can cash it in for $1,000. So our formula for simple interest is that future value is principal times 1 plus RT. R is your interest rate as a decimal, and T is time. So in this case, what we know is the future value. So I'm going to replace the F with a 1,000. That's the future value of this bond. I don't know the present value, so I'll leave that as a P. My interest rate as a decimal is 0.0428, and time is 5 years. And then I just have to solve this thing for P. So I'm going to simplify everything that's in the parentheses first, right? Order of operations. Okay, so I have 0.0428 times 5, and then plus 1, right? Because you do the multiplication first, then the addition, and that's 1.214. So 1,000 is equal to the present value, or the principal, times 1.214. And then how do I finish solving this for P? Divide both sides by 1.214. 1,000 divided by 1.214, and I get $823.72. So that's how much the bond would cost today, and then you can cash that in 5 years from now for $1,000. That make sense? Okay. All right, we're just not going to do this because we're going to talk about credit cards in a later lesson, and so I don't even want you to think about this right now. Okay, so class 22, 10.3 compound interest. So there's a quote that says the most powerful force in the universe is compound interest. It's attributed to Albert Einstein. We're not sure that he said it, but we think so. So under simple interest, only your principal generates interest. So only your initial amount generates interest. But under compound interest, not only does the principal earn interest, but your interest earns interest. Okay, so any previously accumulated interest also earns interest. So money invested using compound interest grows much faster than money invested earning simple interest. So for example, imagine that your parents invest $5,000 at 6% APR, that's yearly interest rate, the day you were born. So let's calculate how much money the investment is worth 1 year, 2 years, 3 years, 4 years later. We're going to use compound interest and T years later. All right, so we'll make a little table here. So I've got the value of, I've got time and the value of the account. So at year 0, value of the account is $5,000, right? 1 year later, it's going to be 6% more. So how do we increase by 6%? Times by 1.06 or 0.06 and then add it to the original 5,000. So I'm going to multiply by 1.06, 5,000. The 1.06 is because I keep 100% of that $5,000. That's the 1, plus an additional 6%. That's the 0.06. So that's $5,300 1 year later. 2 years later. So 1 year after I had 5,300. So the difference between compound interest is that, and simple interest is that with compound interest, in year 2, I would add 6% of the original 5,000, only of the original 5,000. But in compound interest, I get to take 6% of 5,300. So that $300 that I made in the first year, now that's going to work for me too, and I'm going to take 6% of that also. So I'm going to take this 5,300 and multiply 1.06, and I get $5,618. Okay, and then a year after that, I'm going to make another 6% on what's in the account. So take my previous amount times 1.06, and I get 5,955 and 8 cents. For year 4, I'm going to increase that by 6% again, so times 1.06, and I get 6,312 and 38 cents. So let's think about a formula for year T. How could I figure out the value of this account T years from now? Let's say T years from year 0. Yeah, Ryan? $5,000 is what we start with. And then every time we move a year, right, we multiplied by 1.06. Yeah. And multiplying by 1.06 over and over and over again is like saying multiply by 1.06 to the t, right? Repeated multiplication is an exponent. So this is times 1.06 raised to the t. So that would be the formula for the value of my account after t years. So I'm going to predict even further into the future here. Now that I have an explicit formula for the value of my account after t years, let's calculate how much money is in there after 10, 20, 30, 40 years instead of just 1, 2, 3, 4. So in year 0, there's $5,000. We know that. 10 years later, so I've got 5,000 times 1.06 to the 10th, right? Because multiply by 1.06 each year for 10 years. So that means you're going to multiply by 1.06 10 times. That's to the 10th. And I get 8,954 and 23 cents. And I'm always rounding down. Why am I rounding down? That's what banks do. Yeah, they're never going to give you. Yeah, they're not going to give you any extra pennies, even if it's just a partial penny. They always round down. So that if you have a savings account, they're always going to round down. If you're paying them a mortgage payment, they're going to round up. Yeah. All right. So 20 years later, I do the same calculation, 5,000, and then I have to multiply by 1.06 20 times. So I raise it to the 20th. And I get $16,000, $16,035 and 67 cents. Same calculation for 30 years later. You start with 5,000, multiply by 1.06 30 times, which is the same as 1.06 to the 30th. And I get 28,717 and 45 cents. After 40 years, 5,000 times 1.06 to the 40th. $51,000. $50 years. $92,000. And 60 years. $164,938. And 45 cents. So I want to plot these points. I'm going to have time on the x-axis and the value of my account on the y-axis. And I'm going to plot all these points so I can see how fast this is growing. Right? So 0 is 5,000, 0, 5,000. And then I've got 10, about 9,000. I can't be perfect here because my grid isn't that fine, so I'm going to round a little bit. 20, 16,000. So 20. Oops, that was 90,000. Sorry. 10, and that was too much. Sorry. So, the zeros are blurring. 0, 5,000. That is like here, because that first one says 20,000. And then 10 is 9,000, so it's just a little bit higher there, almost at 10,000. And then 20, 16,000. So that's 10,000, about there. Year 30, 28,000. So that's 20, 30, almost to 30,000. Year 40, about 50,000. 40, just a little bit bigger than 50,000. And 50 is 92,000. So that's 90,000, a little bit bigger than that. And then 60 is about 165,000. Yeah, one just goes just off the chart. 160, just a little bit bigger. So you can see that the jump in value every 10 years is bigger and bigger and bigger, right? So from year 0 to year 10, we did not grow very much, right? We went from here to here is not a very big jump. But then my jump from year 10 to year 20 is a little bit bigger. 20 to 30 is even bigger. So we can measure how much it grew, these vertical lines like this. So you can see the jump gets bigger and bigger and bigger each year, how much the value grows by. This is exponential growth because I'm multiplying by the same amount every time. To get from year to year, I multiply by 1.06. So compound interest is an example of exponential growth. And the longer you leave your money growing exponentially, the more it works for you. Yeah, I mean, you might not have 60 years to let $5,000 grow, but if you put $5,000 in for like in this example, you're a parent. If you invest this when your child's born, they're going to have just $5,000 by the time they retire. Now they have $165,000. To get a general formula for annual compounding, we're going to take the formula we generated earlier, right? This 5,000 times 1.06 to the t. Take that formula, and I'm going to replace the 5,000 with a generic amount, right? Instead of saying we invested $5,000, we're going to say we invest P dollars. And we're going to change the 0.06, that 6% interest rate, to a generic interest rate called R. And so our formula for future value of P dollars is going to be P times 1 plus R. Instead of 1 plus 0.06, it's 1 plus R to the T. So this is for annual compounding, if you earn 6% once a year. So for example, if you have $875 in savings, you want to invest it. Your goal is to have $2,000 in 7.5 years. So your local bank is offering a CD that pays an APR of 6.75% compounded annually. What is the future value of your $875 in 7.5 years? Okay, so just write down my formula. Future value is present value times 1 plus R to the T. The present value is $875, so I'm going to replace my P with an 875. Replace the R with 6.75% written as a decimal, which is 0.0675. We just move that decimal point 2 to the left. And I'm going to compound this for 7.5 years. So I'm going to put 7.5 up at the top here. So I just do this all on my calculator. So 1.0675 raised to the 7.5 times 875. $1,428.12. That's the future value of $875. All right, so I didn't reach my target of 2,000, right? I wanted to have $2,000 in there. How much more do I need to invest to meet my $2,000 goal? Discuss. What do you have to make P? What do you have to put in for P to make the future value come out as 2,000? Okay, so in this case, I'm trying to get a future value of 2,000. So I'm going to put in for F my 2,000, and I want to know what P should be to get me there. Solving that equation is beyond the prerequisites for this class. So, doing the same thing to both sides. How to get a variable out of an exponent is kind of a tricky thing. Oh, sorry, T is supposed to be 7.5. Oh, okay, so we can solve this. We can do this. All right, so you could do it by guess and check, but we can also solve it. So if I take my 1.0675 and raise it to the 7.5, I get 1.632. Yes. No. I just started with my F equals P times 1 plus R to the T, and I just plugged in. All I did is plug in the stuff I know. I know future value is 2,000. I don't know P. I know my interest rate is 6.75%, and I know time is 7.5 years. So I'm not doing anything to both sides yet. And then in my next step, all I'm doing is simplifying the right side. I'm still not solving, right? I'm just raising 1.0675 to the 7.5. 1 plus 0.0675 is 1.0675. I just added it in my head. And then I'm going to divide both sides by 1.632. So we get P is 2,000 divided by 1.632, $1,225.49. So if this is your only investment option, if you want $2,000 7.5 years from now, you have to invest $1,225.49 today. Okay, now same scenario as above, right? Except the bank is offering to pay you part of your yearly interest each month. So you're getting more money sooner. So instead of at the end of the year, you know, on December 31st, where they pay you 6% interest, now they're going to pay you a little bit of your yearly interest every month. So plus you're going to make interest. So your interest should earn more interest, and you're going to make interest on that half year. Oh, we shouldn't have gotten interest on the half year because they pay you only once a year if they compound annually. So both our answers are wrong to the previous one. This should just be a 7. Because in a CD that pays annual interest, you get your interest on December 31st. And if you don't leave it in for a full year, you don't get the interest. So these should both just be 7s. Now you know. 1.0675 to the 7th times 875 is 1382. I heard some, why are we doing that? Because if you make annual interest, right, that means yearly, right? So you're compounded annually. That means at the end of the year, they're going to give you interest on whatever amount of money is in your account. So they don't pay you interest until December 31st. So if your money is in there for half a year, you don't earn interest on that until it's been in there for a whole year. So if you take it out after 7.5 years, you've only made interest for 7 years. If you want the interest for the last year, you have to leave it in till the end. Okay, that's how it works when you compound annually. So then this guy is going to be different. So 1.2 to the 7th, and then I have to do, so that's 1.58 if I round it. Divide both sides by 1.58. I get $12.66 is how much I have to invest. All right, so now, same scenario, we're still getting 6.75% interest, but they're going to pay us part of it every month. Instead of just at the end of the year, December 31st, you get all of your interest, you're going to get a little bit of your interest every month over the whole year. So this way, I should generate more interest because I'm going to earn interest on interest more frequently. And I'm going to get, I'm going to make interest on that half a year that I didn't get any credit for before. Okay, so will I have $2,000 in 7.5 years, starting with 875, if I compound monthly? So if this is my yearly interest rate, how could I calculate my monthly interest rate? Divide by 12. Okay, so I have 0.0675 divided by 12 is 0.005625. Okay, so that's my interest rate as a decimal monthly. So that's how much I get to make each month. And I make that for 12 months, so it makes a total of 6.75% for the year. All right, so starting, let's write down my formula. Future value is present value times 1 plus R to the t, but now we're measuring t in months, right? Because we're going to make interest every month. So future value, don't know. Present value, 875. 1 plus 0.005625. And what should I make t? Doing months, yeah. How many months? It's in there for 7.5 years. How many months? 84. Yeah, 7 times 12. 7.5 times 12 is 90. Yeah, so 84 is the 7 years plus 6 months for the half year, 90 months. So I get $875. I make this small amount of interest, like a little more than 0.5% every month for 90 months. Let's see what this comes out to. Future value is 1.005625 raised to the 90th times 875, 1449. So it doesn't get me to my 2,000, but it gets me further than annual compounding did. Right, I only got to 1382 before. All right, so I will not have $2,000 in 7.5 years. But what if I compounded daily? Because then I'll earn interest on interest every single day. So let's just do the same process I did here. This time I'm measuring time in days, right? So I take my yearly interest rate, 0.0675. How do I get my daily interest rate? Divide by 365. It's going to be a small number. Let's see. 0.0675 divided by 365 is, that e to the -4 means move the decimal point 4 to the left. So I'm going to have 0.000185 if I round it. That's my daily interest rate as a decimal, which as a percent would be 0.0185%. Small percentage each day. All right, so now let's write down my formula. F equals P times 1 plus R to the T. Future value, don't know. Present value, 875. 1 plus this interest rate is 1.000185. And T, now I'm measuring in days. How many days are there in 7.5 years? Yeah, let's just uncomplicate the leap year issue. We'll just say there's 365 days in every year. Yeah, so you do 7.5 years times 365 days in a year, and we get 2,737.5 days that we get to earn this interest. All right, so I do 1.000185 raised to the 2737.5. Order of operations says you have to do this exponent before you do the multiplication. So I do that first, then multiply by 875, and my future value, oops, is $1,451.87. So compounding monthly versus daily made me an extra $2. So it didn't get me much closer to the $2,000 goal, right? So in general, this is how you compound P dollars, how you find the future value of P dollars in T years at an APR of R percent compounded N times per year. So this is it written in one concise formula. We did each pieces of this formula in stages. So the very first thing that we did was the interest rate divided by N, how many times we're compounding, right? So we took that interest rate and we divided by 12. or 365, right? So if you were going to compound weekly, you do your interest rate and divide by what? 52. Yeah. All right, and then we wrote this all down, and then this n times t, the number of times you compound times the number of years. So if you're measuring t in years, we did that separately in on the calculator and then put it in the formula, right? This number we got by doing 7.5 years times 365 compoundings a year. How many times you get the interest. So we did these problems without having a formula, but here's a formula, right? So you can memorize it or not memorize it. Do it either way is comfortable. All right, so you try 8, 9, and 10. I want you to compound twice a day, every hour, and every minute. It's not that bad. Okay, so let's go through these together. I will do the first one non-formula, and then I'll do the other two with the formula so that you can pick which one you like better, right? So we started doing these without formulas. And if I want to do this twice a day, I have to start with my yearly interest rate. I make 0.0675 per year. So I make 0.0675 per year. I need to know it's called a periodic interest rate. How much interest do I make each time I compound if I compound twice a day? Right? So how many half days are there in a year? 730. There's 365 in 1 year, days in 1 year. So half days would be 730. So I'm going to take my 0.0675 and divide it by, spread it over 730 payments. Okay, so the bank is going to pay me twice a day for a year. That's 730 times. So you take that yearly interest rate, divide by 730. Okay, so 0.0675 divided by 730, and I get a really long decimal, right? So that is 0.0000925. I just rounded it, yeah. So here's the thing. When you do the calculations in your calculator, don't round them, right? But for the purpose of saving your writing, like you're just writing down so that somebody who reads your work will know what you did, but you don't have to write all these long decimals out because that just feels like a tedious, unnecessary thing, right? So I'm going to round it when I write it down, but when I use it in my calculator, I'm going to use this exact number, right? So I'm not going to retype 0.000925. I'm going to use this number. Okay, so I'm not going to press clear. I'm going to leave it there because I'm going to use it later. So then I have to write down my formula, F equals P times 1 plus R to the T. P is 875. R is this 1.000925. And then I have to raise that to the number of times I'm getting paid interest in 7.5 years. Right? So I have to, this number here should be 7.5 times 730. 5475. That's 7.5 times 730. So it's the number of times you're getting paid interest over the course of 7.5 years. All right, so now I'm going to have my calculator do all of this calculation without any rounding. So I'm going to take this interest rate and add 1. And I'm going to raise that to the 5475. And then I'm going to multiply by 875. And I get 1451 and 64 cents. All right, so if I do this every hour, this time I'm going to use my formula. P times 1 plus R over N to the N T. N is the number of times you compound per year, and T is time in years. So this is going to be, P is 875, R is 0.0675 divided by N, the number of times I compound per year, raised to the NT. And what is N? How many times are you going to compound in a year if you compound hourly? 8,760, and you get that by saying, okay, well, there are 24 hours in a day times 365 days in a year. That's how many hours there are in a year, 8,760. And then your exponent here should be N, 8,760, times time, 7.5 years. So then I can type this all into my calculator. If you have a scientific calculator, it'll know the order of operations, and you can just type it all in. If you don't, if you're using your cell phone or something, just make sure to do this in steps, so following the order of operations. So do everything in parentheses first. So I would do 0.0675 divided by 8760. Add 1. Raised to the, and I should put in parentheses 8760 times 7.5, and then times 875. 1451.67. Yes. Even typing out the whole decimal? Is that what you mean? Maybe it could be that 1.00007705 is all of the decimal that will fit. So it could be that the calculator, it could be that that decimal is longer, and your calculator knows, like, is using the longer decimal. It just can only display this much. That's my guess. Okay, let's do the similar calculation for compounding every minute. So I'm going to write down my formula. F equals P times 1 plus R over N to the NT. And N is the number of minutes there are in a year. If you're going to compound every minute for a year, we have to figure out how many minutes there are in a year. So you say, okay, 60 minutes in an hour times 24 hours in a day times 365 days in a year, and you get 525,600, which you might have already known from the song, right? Does anybody know the song from Rent? Anyway, it doesn't matter. All right, so P is 875. 1 plus my interest rate, 0.0675, divided by 525,600 minutes, to the NT, 525,600 times 7.5. So now I'm going to type this into my calculator bit by bit, following the order of operations and not rounding anything. So I take my 0.0675 and divide by 525,600 plus 1 raised to the, and in parentheses I should multiply 525,600 times 7.5, and then times 875, and I get 1451.67. So there was a rounding thing happened. Yep. So we get the same amount we did when we did every hour. They actually were a little bit different, but it was by fraction of a penny. Yeah, fractions of pennies. So because the bank always rounds down, these end up being the same. So the more you compound, so hopefully the lesson we've learned here is that the more frequently you compound, the more money you get, right? So when we compounded monthly, we got $14.49.61, and then we jumped to daily, we made an extra $2, which doesn't seem like that much, right? $2. But then when we compounded twice a day, hourly, every minute, from twice a day to hourly, we made an extra 3 cents. And from hourly to every minute, we made nothing. We made fractions of a penny. Okay, so the more you compound, the more money you make, but it doesn't grow without bound. Right? So that's one of the remarkable properties of compound interest, is that even if you let the number of compoundings increase to infinity, right? Even if you could compound an infinite number of times a year, the future value approaches some limiting value. It won't grow without bound. So even if we compounded the money 1 billion times per second, the future value would still be no more than that limiting value. And this limiting value represents the future value of an investment under something called continuous compounding. That's if we compound an infinite number of times each year. Okay? And it has a special formula for continuous compounding. And it is the future value is P times e to the RT, and E is this magical number 2.718. You may have seen it in a previous math class. It's called Euler's constant, named after mathematician Leonhard Euler. Showing you where this formula comes from would require some calculus, so we're just going to accept it, right? We're just going to use it, accept it as true. All right, so how much will your $875 make if you're making 6.75% interest, but this time we're compounding continuously, which means we're going to compound an infinite number of times per year. Every possible moment, we're compounding interest, right? So we use this new formula when you see the word continuously. F equals P e to the RT. Plug in what you know. Replace your P with 875. Then we have E, which is just a number, 2.71828. And then R is your interest rate, 0.0675. And T is time, 7.5 years. And I'm going to have my calculator do this. My calculator has a button for E. If yours does, you can use it. And if it doesn't, you can use the number 2.71828. So I'm going to do 875 times. My E button is right here, and it pops up with e to what power? 0.0675 times 7.5. And I get 1451.67, which is the same as I got when I compounded hourly and every minute. So if you don't have an E button, you would type in 875 times 2.71828 raised to the 0.0675 times 7.5. Get the same answer. Okay, so here's a really important concept called the annual percentage yield. So it's also called the APY of an investment, or the effective rate, is the percent of profit that the investment generates in 1 year. So there's the APR, right, which is usually what's advertised, and then there's the APY, which varies depending on how many times you compound. Right? So if you compound once a year, the APR and the APY are the same thing. But the more you compound, the more money you make, which means that you effectively make more interest than the APR. So we'll do an example. If you start with $1,000 and after 1 year you have $1,099.60, what was your APY? So what percentage did your investment increase over 1 year? So remember, percent change from a couple days ago is the amount of change over the original amount. Okay, so how much money did I make over 1 year? If I went from 1,000 to 1,099.60, how many dollars did I make in profit? $99.60. That's how much my investment changed in value. Compare that to my starting amount of $1,000, 1.0996, right? So, no, that's not right. It should just be 0.0996. Did you do 1,099.60 divided by 1,000? Okay, so I just did 99.60 divided by 1,000. So we just have to interpret. Those are two different ways to approach the same problem. You interpret them a little bit differently. This says a 9.96% APY. That's the percent increase on my account after 1 year. Okay. When you got 1.0996, you'd interpret the 1 as I kept 100% and I made an additional 9.96%. So I did show you two different ways to approach that problem. So you can do either way. Okay, you try computing the APY on an account that begins with 835.25 and grows to 932.80. Okay, so we do amount of change. How much money did we make? $97.55 compared to my original amount, $835.25, and it comes out to 0.1168 or 11.68% is my annual percentage yield. That's the percentage of money you make in 1 year. Okay, so this is an important concept to be able to compare bank accounts that have different compoundings. Ryan, be quiet. So which of the following investments is better? So you just want to imagine investing $100 in each of these accounts, figure out how much you have at the end of 1 year, and then calculate the percent increase. That's your APY. Okay, so if I compound continuously, I've got a minute, I can do this. Okay, so investment 1, F equals P, E to the R, T, because I see the word continuously. My imaginary principal is $100. R is 0.067, and I'm just going to invest it for 1 year, and I want to know what it grows to. So I have $100 times E to the 0.067. And I end up with $106.92. Which means that my APY, how much my account grew by, it went from 100 to 106.92. What percent growth is that? 6.92%. That's how much my account grew, from $100 to $106.92. Okay, so then investment 2, I'm going to compound monthly, which means I use this formula, 1 plus R over N to the NT. My imaginary principal is $100. 1 plus my interest rate is 0.0675 divided by 12 because it's monthly to the 12 times 1 because I'm just going to invest this for 1 year. 0.0675 divided by 12 plus 1 raised to the 12th times 100 is $106.96. Right? Which means that my APY is 6.96%. So now you know that 6.75%, even though you're compounding fewer times, is better than 6.7% compounding infinite times. And then I'm going to leave this last one to you.